Welcome to Marine Learn, practical knowledge and training for maritime professionals. Hit the bell button, subscribe, and like the video so we keep bringing valuable content to you. Deep inside the hull, auxiliary boiler number 1 reaches critical temperatures. Heavy metal furnace tubes begin warping and bulging under immense heat stress. This level of tube distortion required sustained heat over time, the result of a documented sequence of human errors spanning the entire fuel changeover. In maritime operations, engine room resource management is the protocol that keeps complex machinery running safely. When that management breaks down, disaster follows. Some of the most severe maritime failures occur when operators blindly trust automated systems and stop physically verifying the data in front of them. The conditions for this failure began taking shape right after the vessel cleared port state control and transitioned out of the emission control area. Here, the vessel crosses the boundary, beginning a fuel changeover from low-sulfur marine gas oil to very low-sulfur fuel oil, handled by junior engineers. Rough weather and heavy rolling impact the sensors, generating wildly fluctuating differential pressure readings on the control room monitors. Rough sea states turn routine fuel changeovers into high-risk operations, placing a premium on manual oversight and situational awareness. Faced with fluctuating data, the junior engineers make a crucial misjudgment. They assume the erratic pressure readings are the result of a faulty sensor, rather than an accurate reflection of the rough sea conditions. This scene breakdown illustrates their operational response. To bypass the automation they believe is failing, the operators switch the boiler into manual mode, but the operators fail to leave the control room to physically check the local gauge glass mounted directly on the boiler. Skipping that physical verification creates a severe operational blind spot. The crew has no actual confirmation of the water level inside the firing boiler, relying exclusively on digital interfaces during an anomalous event. Strips the engineering team of ground truth, leaving them flying blind. Simultaneously, a hidden mechanical failure compounds the danger. The boiler's low water level float is physically stuck, disabling the automatic safety trip that should have shut the system down. Adding to the chaos in the control room, poor fuel atomization during the changeover causes repeated flame failures inside the furnace. As the boiler begins to run completely dry, the exhaust gas high-temperature alarms trigger, filling the room with persistent audio warnings. Confronted with a flood of alerts, the operators experience alarm fatigue. Confirmation bias takes over. Having already decided the sensors are faulty, they actively ignore the critical temperature warnings. Acting on flawed assumptions, the engineers continuously fire the boiler manually, forcing flames into a chamber that lacks sufficient water to absorb the heat. The physical consequences of dry firing are immediate. The intense heat causes massive overheating, cracking tubes 2 and 25 and causing widespread bulging across dozens of others. Safety alarm systems serve no purpose if the human operators systematically write off every warning as a false positive. The investigation identified the stuck float and the DP cell's erratic readings as technical failure points, but the disaster stemmed from how the crew processed that data. The root cause was human error. Poor watchkeeping discipline and improper operational judgment drove the engineering team to destroy the very equipment they were trying to run. This reveals a failure in supervision. Senior engineers were absent from the control room during a high-risk fuel changeover in a high-stress environment. Technical redundancy and mechanical failsafes cannot compensate for a total breakdown in operational hierarchy and team communication. The most immediate operational correction is straightforward. Mandatory physical verification of the gauge glass is required. Before any manual firing of the boiler, systemic fixes must follow. Maintenance schedules require strict alignment. Differential pressure cells need regular renewal, and alarm testing must be rigorous and fully documented. These practices are not optional. They are necessary to maintain mandatory compliance with SOLAS and the ISM code. Under international maritime law, crews are required to investigate and respond appropriately to all abnormal conditions, rather than muting them. Sophisticated shipboard automation provides a layer of safety, but when sensors fluctuate and alarms sound, the crew's physical verification remains the final line of defense. Learn, simulate, master the sea.